Okay, hello everyone. Hello everyone. Okay, in this video we are going to keep talk about the deflection calculation. Okay, in the previous video I just give you the big picture of the deflection calculation. Okay, just the in this type of problem, okay, when we apply a load on a beam, okay, we want to know what's the deflection or the elastic curve of the beam. Okay, so we need to use the differential equation to solve the elastic curve. Here is the differential equation, and we also need a boundary condition. Okay, to solve the elastic curve or the deflection. Okay, here to solve this differential equation, we need to know the moment function. But actually, for this type of problem, we rarely get a moment function directly. Okay, okay. We often have to give. We often the situation we often face is it give you the loading function. Okay, and then you have to integrate the loading function twice to get the moment function, then to solve the ordinary differential equation. Okay, and now for this video I will discuss with about the how to represent the loading function by a discontinuity function. Okay, we need a mathematical tool called discontinue function. Okay, but this continuous function, it has some name. Okay, in this textbook, there's a name for the name for this discontinuity function is called Macaulay functions. But I would rather call it a discontinuity function. Okay. Okay, here's the definition of this discontinuity function. Okay, the discontinuity function, we will use the bracket. Okay, here is a bracket, and x minus a, put in x minus a here, and his power n. Okay. Okay, so this is the definition of the discontinued function. Okay, that means if your x is minus than a, this all function is 0, and your is equal to a or greater than a. That means your function is x minus a to the power n. Okay, actually, this function is very similar to the unit step function in your engineering mathematics 1. Okay, it's very similar. I think almost identical. Okay, so, but unit step function is in time domain. Here is in x domain. Okay, I think that's the greatest difference here. Okay, and now I have now the following is the integration rule for the discontinuity function. Okay, yeah, yeah. I just say when trying to solve this problem, we need to do lots of integration. Okay, so here I have to show you the integration rule for the discontinuity function. Okay, and the integration rule for this continued function, it's all about the power of the discontinuity function. Okay, the power is very critical here. Okay, if your power n is equal to -1, -2, or -1, okay, and then your integration is just keep this function and add the power, add 1 to the power. Okay. Okay, what does that mean? Is I think you can say like this. Okay, so which color should use? Okay, so for example, so, boy, what's happening here? Oh, what's happening here? Oh, this one. Okay. Okay, so that means if you are x minus a, okay, minus 2, do the integration. Okay, it's equal to x minus a, and just add the 1 to the power, so it's become -1. So if you do the integration for x minus a power -1, okay, that's just equal to x minus a, okay, and add 1 to the power is equal to 0. Okay, that's when your n is become -2 and -1. Okay, when your n is -2 -1, that's the integration rule here. Okay. When your n is equal to 0, 1, 2, 3, okay, let's rule it will have at least some difference. For example, if your x minus a to the power n 0 to dx is equal to x minus a 0 plus and 0 plus 1 and can equal to 1 and 1 over 1. Okay, that just equal to x minus a to the power 1. Okay, you see, this rule is very similar to what you learn in the calculus class. Okay, okay, okay. The integration rule for the polynomial, right? Okay, this is just exactly the same when your n is 0, 1, 2, 3. Okay, so similar. So we can raise another example is x power 1 to the integration is just equal to x minus a 1 plus 1 and 1 plus 1 is 2, so it's 1 over 2. Okay, so if it's x minus a to the power 2 dx is equal to, okay, x minus a and 2 plus 1, okay, and 2 plus 1 is 3 also, so it's here. Okay, so you see this is just exactly the same to extend to the calculus, right? Okay, okay, but be careful when your n is minus 2 or minus 1, the integration rule is different. Okay, so this is a rule you have to follow. Okay, because in this course we don't want to give you the very detailed derivation. Okay, just let you know the rule. Okay, and then you can use the rule to solve the problem, and that's fine. Okay, that's all, and that's the goal of this course. Okay. Okay, so this is in the definition of Macaulay function or discontinuous function and integration rule for the discontinuity function. Okay, so why we need this discontinuity function? Because we need to use this discontinuity function to represent or to describe the loading function. The loading function. Okay, okay. In this chart, it gives you I think the most common situation for the loading of the beam. Okay, and this is called concentrated moments. Okay, this is called concentrated force. Okay, or concentrated force. Yeah, because this moment and force is acting on a specific position, so it's called concentrated moment and concentrated force or loading. And the next two is just what we learned at the beginning of this class. It's called distributed load. Okay, okay, okay. And then we need to use the discontinued function to represent this loading, and then we have to integration the loading function twice to get the moment function. Okay, that's why we need the integration rule. Okay, and from this chart you can see this integration rule is just what I just described here. For example, let's look at the bottom. Okay, okay. Here your loading function is my discontinuity function power 1. Okay, its power is 1. It's equal. So that means the integration rule is the same as what you learn in calculus. So it's 1 plus 1 equal 2, and then move to and when 1 over 2 here, and you do further integration. This is power 2, and then do integration again. The power becomes 3. Okay, and move the 3 down here, so it equal to 2 times 3, so equal to 6. Okay. Okay, so and then when you are in the loading function, the x minus a is power is minus 2. So okay, just add the 1 to the power. So this minus 1, and then just integration is just add the 1 to the power. So it could become the power 0. Okay, okay. Just be careful the integration rule. Okay, it's different when your n is minus 1 and minus 2. Okay. Okay, and next thing I want to explain something. Okay, explain something. Okay, let's say okay, let's this video I want to explain why the represent the concentrated load and concentrated moment by a discontinuity function. Okay, here is the explanation from this textbook. Okay, but this is not a very rigorous proof. It's kind of like an intuitive derivation. Okay, so Okay, so it's not very rigorous proof. Okay, so just see if you can accept this. Okay, or if you don't, or if you don't like this intuitive derivation, you can just memorize the result. Okay. Okay, so here is okay. Let's start with the explanation here. Okay. Okay. Okay, let's see. Okay, so the concentrated load, that means this load is acting at a certain point on a beam. Okay. Okay, here I also want to address the point is the W is called a loading function. Okay, the unit of a W, okay, let's say the Wx, okay, it's a unit. Okay, what is unit? Okay, its unit is Newton per meter. Okay, that means it's force per length. Force per length, ENGTH. Okay, so it's actually I say this before, so it's called intensity. Okay, intensity. Okay, the loading function, its unit is force per length. Okay, it's newtons per meter. Okay. Okay, let's say, okay, let's back to the concentrated loading. The concentrated loading, okay, this concentrated loading at its position here. So we can see this as the concentrated loading is this force acting on this tiny length called epsilon. So that's why this slide say write this P. Okay, okay, W is equal to force divided by length. Just like what like this is just what I say. The W is the unit of W is intensity. It's force divided by length. Okay, the force divided by length epsilon. The epsilon is a very small value. Okay. Okay. So and then we replace this epsilon by the discontinuity function. Okay, discontinuity function. Okay, then you can see, okay, you will see you can see this here. Okay, it's p times x minus a power minus 1. Okay, okay, this is, I just said, this is a very rough, very intuitive derivation. Okay, to see. Okay, to see. Okay, I'm not sure you can accept this or not. Okay, I think this is very intuitive derivation. Okay, so that's why the concentrated load, its power is minus 1. Okay, because it's a force per meter. Okay, force per meter. Okay, so this. Okay, so the Macaulay function is power minus 1 because it's at the denominator. Okay. Okay, so the loading, this concentrated load, okay, you represent it by the discontinuous function like it's like this p times x minus a to the power minus 1. Okay, that means when your x is minus a, the whole function is 0. Okay, don't think in this way. If maybe you can think, oh, it's because of p divided by minus p divided by 0. No. If x minus a, that means the whole function is equal to 0. If x is equal or greater than a, it's p times, okay, p times the x minus a to the power minus 1. Okay, that's for concentrated load. Okay. Okay, let's look at this. Another situation is concentrated moment. That means the moment is acting on a certain point on a beam. Okay. Okay, so here is the derivation. We can see the moment as a couple, okay, a force, a moment, a couple moment. Okay, so okay, let's just write this. Okay, here. Okay, if the position is here, it's called XA. Okay, the moment can be seen as there's a force here, it's called P, and there's a force here, it's called P, and here is epsilon over 2, here is epsilon over 2, and here, sorry, here, okay, here is, okay, here is also epsilon over 2. Okay, here is also epsilon over 2. Okay, and here's our reference point. Okay, our reference point is at A. Okay, the moment is equal to, okay, the moment here, okay, because it's clockwise, so let's call it minus 0, m0 is equal to, okay, it's equal to, okay, the force acting, there is a force, there is a force very close to A, and distance is epsilon over 2, and there's another force here, and its position very close to A, and its distance is epsilon over 2. So okay, so these two forces will generate clockwise moment. So it's equal to P times epsilon over 2. Okay, and P times epsilon over 2, and it's all negative. So it's equal to minus P times the epsilon. Okay, okay, so and then we will reach a conclusion that m0 is equal to P times the epsilon. Okay, okay, I will use this to explain why the moment, the power of the moment is -2. Okay, and don't forget okay, don't forget the unit of the W. Don't forget the unit of W is force divided by length. Okay, okay. The moment can be see there is a force. The moment can there is a force acting here. There's another force acting here, and then to create a moment. Okay, okay. So, okay, the force here. Okay, the force in here is also a concentrated load. Okay, so the force here when we use the when we try to use the intensity function to describe the force, it's equal to force divided by the length epsilon. Okay. Okay, this also a constant can be viewed as a concentrated load. Okay, force divided by the length. Okay, and always and then we all also know from this conclusion we also know the P equal to m0 divided by epsilon. Okay, so it's equal to m0 divided by epsilon, and this also epsilon, so it's equal to m0 divided by epsilon square. And then we replace this epsilon square by the discontinued function. So it will become like this. It's x minus a to the power 2. Okay? Okay? Okay, so this will become here. Become here. It become here. Okay. Okay, it's a moment times the x minus a to the power minus 2 because it's actually m naught divided by x to the minus a to the power 2. Okay, because this is at the denominator, so that's why it's minus 2. Okay, that's why it's power minus 2. Okay, so this is also a very intuitive derivation. So okay, so let's wrap up. The conclusion is if you have concentrated load, your discontinuity power is -1. If you have concentrated moment, your power for the continuity function is -2. Okay. Okay, so okay, that's the most important conclusion here. Okay, and then there's another thing you have to notice that okay, I wrote it here minus m. Why I write this? I write this. Okay, okay. So don't forget in the previous section, in the shear moment diagram, in shear moment diagram section, we say actually the shear moment diagram, the moment is the internal moment. The moment is the internal moment. Okay, okay. Here is the same thing. The moment we want the internal moment. We want the internal moment. Internal moment. We want the internal moment. Okay. The m0 here is the external moment. External moment. Okay. Okay, the external moment, okay, it's clockwise. That's why it's minus m0 because it's clockwise. Okay, And the internal moment is a reverse direction or just opposite to the external moment to reach the rigid body equilibrium. That's why for the internal moment we also need add the minus in front of the external moment to get the right sign. Okay, okay. So that's why overall is equal to m0, m0, right? Okay. So here be careful. The moment here the moment we need is an internal moment. Is an internal moment. Okay, that's why there's a minus sign in front of this m and a minus m here. Okay, because this external moment is minus m. Okay, but now we want an internal moment, so we have put another minus sign in front of the external moment to get the right sorry, we have to put a minus sign in front of the external moment to get the right internal moment. Okay, so be careful this moment, the moment function. Okay, that's very important. If you miss the sign, the calculation will be you will be have a huge problem on calculation, or especially for results. Okay. Okay, so let's review the conclusion for this video again. Okay, for the concentrated loaded, the power is -1. The concentrated moment, the power for the continuity function is -2. And then the moment here, don't forget we are talking about the internal moment. That's why you need a minus sign in front of the external moment to get the right internal moment. Okay, okay. I think I can wrap up. I can stop the video here. Okay, I think I don't want to make the video too long. Okay, and then for the next video, we'll also talk about discontinuity function. Okay, there's still some point in the discontinuity function. Okay, so I stop the video here. Okay, see you in the other video. Bye bye. Hopefully it's not too bad.